Hello, everybody. Today I'm going to do a little screencast thing because basically I want to read along with you in the textbook. Um, I'm going to recommend that you go back and read this section yourself. Maybe you know make some notes about the some of the things it says. It's a lot of really good, solid advice on what to do and not do when writing a proof. So it begins at the bottom of the exercises for the previous section. Direct proof and counterexample 2, writing advice. Um, I like this quote from Gauss here. It is demanded for proof that every doubt becomes impossible. Um, it is demanded, but rarely do we attain to that level of certitude. Usually, there's some questions we leave unanswered in a proof because they seem obvious enough, and where that dividing line is between what you'll where you'll put in explanations to explain a point and where you'll leave them out. It depends on really on the level of the audience you're at. So that's a point I don't believe they make very well in the EP book. That a lot of communication is different depending on the audience involved. All right, so let's just get rolling. I want to go through each of these pieces of advice, um, or directions they call it. Well, so the first one is maybe obvious, but maybe some people wouldn't do it. Says copy the statement of the theorem to be proved on your paper. Make sure the theorem is there along with the proof. So as you're doing the proof, you can refer to the statement that you're trying to prove. And also, if somebody later is reading it, like say a professor is trying to grade it, it's nice to know what you were trying to prove while you're reading what you wrote. Um, Mark the beginning of your proof with the word proof. I usually like to underline it or put a colons after it, make it in bold if I'm doing typeset stuff. Something to indicate to the reader that this is the beginning of one of these formalized arguments, so that they know they're expecting to begin reading stuff that's in a very formal style. Make your proof self-contained, especially if you're doing one sequence after another of proofs. You may be tempted to refer to stuff that you did in a previous proof, and um, while in general that's actually okay, I think this is good advice, at least for beginning proofwriters. Um, One place where this is not necessary is if we've proved something already. One of the more basic facts, it's already been done. You don't have to go back and reprove that in the midst of another argument. I'll give you an example. If suppose we in fact did prove that the sum of an odd number and an odd number is an even number, you can just use that from now on. You don't have to go through the sort of a mini little proof, which would be what the explanation of that step would be. Um, in the midst of any of your current arguments, you could just say, by previous result, we know the sum of these two odd numbers will be even. And so that's a place where you're not completely self-contained. Another place where you won't be self-contained is references to the axioms. Right? If you've got one of the axioms, you don't have to. Well, you in fact can't prove that thing. So you refer to an axiom by just reference. You don't have to include the statement there. Um, Definitions are similar. You expect that everybody reading your proof knows the definition of, say, what it means to be a prime number or what it means to be odd. So those definitions don't have to be stuck into your proof, but the main body of your argument should be self-contained with these few exceptions. Write in sentences and recognize that sentences always have a verb. In sentences that include mathematics, that verb is often is equal to or equals. Right? That's okay. So this symbol right here, the equal sign, that's a verb. Is this a grammatical sentence? Then m plus n equals 2r plus 2s, which is equal to 2 times r plus s. That's a grammatical sentence. And it even remains grammatical if you put in these little appositive phrases that tell you why those things work. Then m plus n equals 2r plus 2s by substitution. That'll be set off with commas or parentheses, which is equal to 2 times r plus s by factoring out 2. Well, that reads well. So this is a sentence with 2 verbs in it. Where? Actually, 3. Theorem 4.1 contains the sentence. No, I see. We should just look at this part of it. Okay. Anyway, yeah. Try to be grammatical. Number 5 here. Keep your reader informed about the status of each statement in your proof. There's sort of 2 things really to watch out for, and they list them both in here. One is you're going to have certain statements that are suppositions. Just make sure that you tell people, right now I'm supposing X, and I don't know what X is, but you just want to keep them clued in that you're trying to reason from some beginning point. There's a proof style we're going to look at in a little while called proof by cases. Well, proof by cases is kind of what it sounds like. You have different cases and you basically prove the thing in each case. A real common one is even or odd. So if I have a statement that works via proof by cases, part of my proof is going to say, suppose X is even, then blah, 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 blah. And I prove it in the case that X is even. Later on, usually marked off so that people understand this is the other case, you'll say, now suppose X is odd, blah, 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 and eventually get to the statement you want to prove in that case. And if you can if you can get both even and odd to end up getting you the statement you're trying to prove, you're done. That's what proof by cases is about. Anyway, those are both suppositions that are subparts of an argument, and you're going to let people know that by writing suppose or assume. Yeah. The other situation that comes up a lot, it's a tendency we have that we like to write down the thing that we're trying to get to, which is fine, except if you don't do anything but that. You see, if you're trying to argue to the point that decides that X is prime, and you write down X is prime, people are going to look at you like, what is wrong with this kid? You gotta get to that. You've got to do some reasoning to arrive at X is prime. But sometimes you still want to write that down. You just need to tell the person who's reading your stuff why you're doing that. This is called a we want to show sentence. WWTS is how I usually abbreviate it. We want to show. Some people say WWS. Want to show. No, what is it? WTS. Want to show. I don't care. As long as you set it off in some way to let people know this isn't something I think is true. It's something I want to show is true. We want to show that X is a prime number. Perfectly fine. X is a prime number. The conclusion of the argument, just right there at the beginning, that looks weird. All right, so let's do some more stuff. Each time you make a deduction, you should give a brief explanation of it. It doesn't have to be huge. There's even times when I think you don't have to do this if it's simple enough. If you end up getting 2 even numbers and you're trying to prove something about their sum, you can say that the sum is even without having to put that explanation, because we previously proved that the sum of 2 even numbers is even. It gets cumbersome to have to do that for every little tiny detail. But for the most part, you should imagine that if you have younger siblings, there's a phase in kids' lives, like I think they're 4, maybe 5 years old, when every other word out of their mouth is why. And they usually have that high-pitched, whiny voice too. So it's why. That's what you have to imagine in your head. You've got somebody next to you going, why? So you write down why. If you feel like instead of writing down why, you should smack the kid who's annoying you, then that might be one of the ones that's too obvious, and you don't really need to put down the explanation. But it's a good practice to at least know for yourself that you could provide an explanation. Even if you decide, okay, I don't think it's necessary, I'm going to leave that one out because we're getting past that level of simplicity now. Could you fill it in? And if you can't honestly say to yourself, yeah, I could fill in the explanation for that step, then go back and fill it in. If it's at all in doubt, then it's not of the level that you get to just elide it. You have to put it in if there could be a doubt. Let's see. This is really good advice that people tend to overlook. There's lots of little connectors that people use in writing, conjunctions as they're known, and I don't mean conjunctions like the and symbol. I mean conjunctions in the conjunction junction. Wait, have you kids even seen Schoolhouse Rock conjunction junction? Well, if you haven't, go check that one out on YouTube. It's amusing. Anyway, the words that we use as sort of the glue to put different pieces together. There's lots of them, and it helps if you mix them up. A lot of people end up picking thus and just doing thus, 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 right on down the line, and it gets boring. Your writing rather should be, well, like any writing, you don't want to be so repetitive that you drive people nuts with it. So there's tons of words they're giving them in here, because, since, then, that if you got a deduction followed by another deduction, then is a great connector in there. Thus, so, hence, therefore, consequently, it follows that. These are all great little phrases you can use. Don't drop them entirely, and mix them around. Sometimes, this next paragraph is a great point. Sometimes you're doing your proof, and you realize, I need this other thing, and I know this other thing is true, but I forgot to introduce it earlier. Ideally, you put your hypotheses up front, but you can always throw one in the middle by going, by the way, notice that blah blah blah, whatever it is true. Observe that, note that, recall that if you think it's something that was done previously and that they should know. Okay. Display equations and inequalities. Let's just show you what is meant by that. Is there a spot in here where they've done it? That is a displayed equation, except for the word then there. See how it's more or less centered on the page? Often in the margin, there'll be a number associated with it, so you can refer back to equation 3.7. Put that number out there. But this is a little bit odd because they've displayed the equation and then they put some words around it too. Let me see if we can find one back in. Oh, I didn't. Freak. I only scanned so much of the text, so I can't look at the previous chapter right now. Well, you get the idea. A displayed equation is one that appears centered on the page. It's not in the midst of the sentence. It's like you break a line, put it in the center of the page. After you're done with the equation, you break the new line and continue on with your sentence. Or maybe not. Could be the end of the equation is where the period goes. Just depends. By the way, I'll note that's a thing that you should recognize. A lot of times in displayed equations, that's the end of the sentence. So there needs to be a period there. See how there's a period on the factoring out too? All sentences have periods at the end, even if the sentences are math sentences. Okay. Now, what can you do? You don't always need to do this. You don't have to do it 100% of the time. It's for more interesting equations. If you're just going to say, x is odd, so x equals 2k plus 1, I think you can put that right there in the midst of the sentence. The most popular typesetting software, if people want to, maybe, and I actually recommend this as something to play with. You can get a free account at a site called Overleaf. So this prevents you from having to put an installation of this software on your own system. The version of it that's on Overleaf is quite good and has all the features you need. But what Overleaf actually provides is access to a system that is called LaTeX. It's got that funny camel case capitalization scheme as part of the name. Tech, this guy, was written by uh, Donald Knuth. And I have to put in a plug for this guy. He's a mathematician, but also a very competent computer scientist. He wrote The Art of Computer Programming. It's a long title. And now I think there's 5 volumes of this. It's a big book, but it is a absolutely essential reference for somebody who wants to be a programmer. It's got lots of examples, lots of fantastic advice on how to write well. If you want to consider yourself truly a software engineer, you have to have that on your bookshelf. I can't compliment it enough. It's really a great book. Donald Knuth wrote this system Tech, and as a matter of fact, he wrote it mostly just as an example of something that would involve a style of programming called literate programming, which just basically means there's a mechanism for enforcing that good comments are written into the code as you go. And Tech is arguably the most bug-free programming system that there is. I mean, I would be surprised if the systems that control nuclear missiles are more bug-free than Tech is. It's been it was written by one of the best software engineers of all time, and it's been poured over by a huge community of math and physics and computer science people. So yeah, Tech is good stuff. The system on Overleaf, though, is called LaTeX. That the law there comes from another person's name, Leslie Lamport. And what he did basically is write a whole bunch of macros in the language that Tech essentially creates a language as well as doing a processing system for that language. And anyway, LaTeX macros on top of Tech make this pretty decent system for typesetting scientific work like math and uh, well, lots of stuff, chemistry, physics, all the I imagine computer science as well. The one truly comp sci journal that I subscribe to is an IEEE journal, and I guarantee the articles in it are all typeset in Tech, and that means the authors had to write, or rather LaTeX. They, the authors had to provide that LaTeX file. The, the approach here is just a bit on the old school side. It's you write a source code into a file, then you run a processing program on that source code, and it outputs graphic stuff. So it's not what you see is what you get. You have to learn to put input codes in. Now, this whole discussion was to get down to math in LaTeX. Because there's 2 ways to do it. You can write a $sign and then do some stuff that would get you math. That's supposed to be a 2, not a Z. And then another $sign ends the thing. So you might have words before this. Say, thus, x squared equals y, which is blah, blah, blah. So that's called inline. That's an inline equation. If, on the other hand, you wanted to say, thus, whoops, you wanted it to look like this, x squared equals y, be displayed math, which is, and again, dot, 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 who knows what's coming after that. If you want it to look like that, you use a different delimiter. You use a slash and a square brace. Right here, I'm trying to show what code would produce that output. Slash square brace, x to the second equals y, and then slash closing square brace to end it. This is sort of typical in languages like HTML or XML. You'll see begin tags and end tags. This is less typical. The $sign thing lets you I mean, you've got the same delimiter at the beginning and at the end. And if you forget one, it'll treat all the words that come after it as math, which basically means it thinks you're writing a whole bunch of variables written together. It looks like it turned italics. So uh, that's actually sort of a poor choice to have a delimiter that's the same at both ends, because it leads to this easy opportunity for getting things wrong. Of course, it's usually easy to fix it. But I do prefer when languages are, yeah, the language specification differentiates between the begin tag and the end tag like this. Anyway, display math, inline math. That's what we're talking about here. When you are writing your proof, you can sometimes put little pieces just inline in the paragraph. More often, though, you're going to want to display it on a separate line by itself, centered, because you draw attention to the math of the argument. I'm not going to talk about this very much, variations. You can read it if you like. They're just trying to get you to understand that even though these are formulaic, proofs are very, there's a set way they're going to go. There's still room for people to do them differently. Um, for instance, one of the things that is different is where do you draw the dividing line between the statements that you feel need explanation and the ones that you think you can get by without explanation. But let's push on after that and talk about common mistakes, because there's a bunch that are really important. This is not a mistake, it's a cardinal sin. If you show me that something is true by stating a couple of examples, I will become angry. Literally. You'll see my face turn all red. Steam comes. No, uh, it's just not done. You can't, in fact, you can't do it. If you give me examples, I can say, well, fine, but what about after that? Does that is there any reason why the examples couldn't be true for these first few small cases and then not be true later on? See, examples stink. They don't do anything. When there's a universal sentence and you try to prove it by an example, usually that means you have to provide an infinite number of examples, which most of us don't have time for. Um, they're giving an example proof here. Consider the following proof that the sum of two even integers is even, something we've done. This is true because if m equals 14 and n equals 6, which are both even, m plus n equals 20, which is also even. Yeah, no, that's evidence that it's true, for sure, but it's not the whole thing that shows you it's true. That's one out of infinitely many cases of two even numbers adding up. I get that it's true, and we all know that it's true that even plus even is even, but that isn't what establishes it. The argument we did last time is what establishes it. Another biggie, I tried to make this mistake in class. I'm pretty sure I made this mistake in class. Remember, I had to X out a whole big section of proof because you guys didn't stop me in time? I'm blaming you because could have been my fault. Anyway, you sometimes get in the habit of using the letter that appears in the definition. Like the definition of odd is that x is equal to 2k plus 1 for some k in the integers. So every odd number, it has to be 2k plus 1. But if you got two different odd numbers in your proof and you say they're both equal to 2k plus 1, you just accidentally set them equal to one another. And that's not staying generic, right? You like the odd numbers to be generic, arbitrarily chosen odd numbers. So they're giving an example. Well, they're giving the same example I just did. Suppose m and n are any odd integers. Then by definition of odd, m equals 2k plus 1 and n equals 2k plus 1. No. Get a new letter there. 2k plus 1 and 2l plus 1. And then you'll have to say where k and l are integers. But you're okay using the definition twice in one sentence. If you see me write on any of your proofs this JTTC, this is what they're talking about, jumping to the conclusion. So what does that mean? Basically, it means skipping steps. you know you want to get to the conclusion. You know what the conclusion that you desire is when you're writing a proof, so you just write it down. But the stuff you have done so far doesn't justify that writing of it down. Then you jump to the conclusion. Does this one really work? Let's see what they said in here. We're doing the proof that the sum of any two even integers is even. That's an easy proof, right? Suppose m and n are any even integers. So far, so good. By definition of even, m equals 2r and n equals 2s for some integers r and s. Then m plus n equals 2r plus 2s. So m plus n is even. I'd almost get it. I'd almost give it. But there is a step missing, isn't there? We're supposed to say this is also equal to 2 times r plus s. And furthermore, we're supposed to note that r plus s must be an integer. So then we've written m plus n in the form that the definition of even needs. You've written m plus n equals 2 times something, and that something is an integer. Then you're all good. But as it stands, you've jumped over a little bit there. I would say this is mild, but it's, at this stage, I just want you to recognize what jumping to the conclusion will look like. This is a bigger error, assuming what is to be proved. Surprisingly, people do it fairly frequently. To assume what is to be proved is a variation of jumping to a conclusion. Well, I would say not. Jumping to a conclusion usually looks like a well-formed argument. It's just, about halfway through, you come to the end. Assuming what is to be proved means you jump right to the end. The first sentence you write down is one of your things, is the thing you're trying to conclude. That's not going to hold much water, will it? So let's look at the example they've given. The proof, the fact that the product of any two odd integers is odd. Okay, yeah, suppose m and n are any odd integers. When any odd integers are multiplied, their product is odd, hence mn is odd. Yeah, you see what they did there? They didn't do the work. They just asserted something that we don't know whether it's true or not still. Actually, I guess we do know, but in that case. But sometimes, sometimes things are still in doubt. I'm trying to think what they're trying to go after here. Confusion between what is known and what is still to be shown. Well, that's certainly an issue that we should keep in mind, right? We need to know what things have we already established as part of our argument and what things yet remain to be proved. Well, let's follow this example and see what's wrong with it. Suppose m and n, okay, wait a minute. What are we trying to prove? The product of any two odd integers is odd. Suppose m and n are any odd integers. We must show that mn is odd. That's fine. They use the phrase "we must show that" up front, so clued us in that that's the goal. This means that there exists an integer s such that mn equals 2s plus 1. I'm okay with that. I think I might prefer it if that was in one sentence. We must show that mn is odd, which is equivalent to there exists an integer s. Okay. All right, where to go here? Also, by definition of odd, there exist integers a and b such that m equals 2a plus 1 and n equals 2b plus 1. That's okay, but I think I wouldn't introduce that with the word also. I would say, since m and n are odd, by definition of, and then go on from there. Then, mn equals 2a plus 1 times 2b plus 1 equals 2s plus 1. Well, how did we get there? Well, there's a big arrow pointing at it. At this point in the proof, we do not know whether there is an integer s making this equality true. In fact, that is one of the things that we wanted to show, that such an s exists. So how could we fix that? I just feel like we should fix it while we're at it. So we have that m times n is equal to 2a plus 1 times 2b plus 1. Well, this is, they have really skipped a lot of steps, haven't they? Let's FOIL rule that out. You'll get 4ab, and then out outer times outer is 2a, inner times inner is 2b, and last times last is 1, which is equal to 2 times something plus 1. What's the something going to be in there? It's 2ab plus a plus b. Okay. Now from there you would say something like, note that 2ab plus a plus b is an integer. That is true because of the closure axioms for the integers. Both the addition and multiplication closure axioms. I'll just refer to them as a group. And that means that Mn satisfies the definition of odd. Oops, I'm spelling bad. That strange looking thing is supposed to be an S. Satisfies the definition of odd. I'm getting the last of the ink out of this pen. That's why that's so hard to do. All right, I'm going to throw this one away now. So yeah, it could have been salvaged from there, but you certainly, you can't jump to this. We don't know that yet. What is the S, by the way, that we do now know? It's this thing. I didn't choose to name it, and some people like to name the things. I prefer to just leave them. Well, it depends, but in this case, I prefer to just talk about that quantity, 2ab plus a plus b. If you like to call that S, be my guest. But whatever it is, it's an integer, and it's in the right spot in a formula that tells us that m times n is odd. Use of any when the correct word is some. Yeah, aren't any and some kind of similar in phrasings, but well, here's the example of the uses that's wrong. Suppose m is a particular but arbitrarily chosen odd integer. By definition of odd, m equals 2a plus 1 for any integer a. For any integer a? That would mean I could put in 17 there and get it. I could put 11, get it. And those aren't going to give me the same thing. M, so that's not right. Any is saying it's universally true. I could plug in any value of a, and that would be what m is equal to. We didn't mean that really. I would say an integer. That's okay. So if you could just chop off that y on the word any, you've got it. Or for some integer, that's probably even better. Best is actually to stick it up front. By definition of odd, there exists an integer a such that m equals 2a plus 1. I actually prefer my quantification and the variables associated with them to go up before the statement if possible. Yeah, so we don't want to do that. Another common word to misuse is the word if. Usually when people misuse if in a proof, what they really mean is since. Well, let's look at that example. Suppose p is a prime number. If p is prime, then p cannot be written as a product of two smaller positive integers. Nothing wrong with that sentence. It's true that if p is prime, then p cannot be written as a product of two smaller positive integers. But how it fits into the argument is a little odd. You see, the sentence right before it, you said, suppose p is a prime number. And then you said, if p is a prime number, like you're in doubt. You just said it was prime, and now you're on, well, if it was, then I would do this. No. So what you mean there is since. Since p is prime, p cannot be written as, yeah, that works. But if is going to, it gives your reader the impression that you're not sure yet what the status of p is. But when you've gone ahead and supposed that it's prime, why would you not be sure? Okay, so then they go on to do some examples. I think we're going to return to the whiteboard for those. All right, so I'm going to go through example 4.2.1 from the textbook now. And then that'll be the last thing we do in this section about writing advice. But I wanted to follow the advice given in the book. The very first thing it said is copy the theorem down onto your page. So I did that before I started the camera. Cool? Now what's next? Well, if I thumb back through the writing advice, number 2 in the writing advice said, clearly mark the beginning of your proof with the word proof. So let's do that. Proof. Fine. Now I'm going to go ahead and prove it. We'll look at this statement. What is our first sentence going to be? Our first sentence usually is just to lay out what hypotheses we get to work with. So what hypotheses are we going to have here? Well, what I'm trying to do is say something about the difference for any odd integer and any even integer. That's when we do the generalizing from the generic particular notion, it means I'm going to say, well, let's suppose we have a particular but arbitrarily chosen odd integer and a particular but arbitrarily chosen even integer. So suppose x is odd and y is even. Watch me have used different letters than they did in the book. Of course, they used A and B, whatever. Suppose x is odd and y is even. By the definition of odd, what does x being odd tell us? There is a case so that x looks like 2k plus 1. And k is going to be an integer, right? There's an integer. K such that x is equal to 2k plus 1. I'm not liking what I wrote here. I had to stop and think about it. Well, I just followed what they did in the book, but I don't like this because I believe this sentence should begin with the word since, not with the words by the definition. So let's fill in how that should be. I should say, since x is odd, I don't know if I can fit it in here. And that would be a capital S there, wouldn't it? So since x is odd, by the definition of odd, there is an integer k such that x equals 2k plus 1. Now I'm happier with it. Similarly, but not quite the same, since y is even, there is, I'm just going to skip the positive phrase. There is by the definition of odd, or of even now, but because I think it's clear, it's a parallel structure. So since y is even, there is an integer k. No, I'm just messing with you. It's not going to be k, is it? If I made that k, then x would be 1 bigger than y. Because y would be 2k, x would be 2k plus 1. I can't use k over again. And that's one of the pieces of advice they had in there in the section about common mistakes. Don't get stingy about the letters. There's dozens of letters out there. Let's use L. I like to make my L's look like a cursive L so you can tell they're not ones. There's an integer L such that y equals 2L. I'm going to have to continue at the top of the board with this train of logic we're after. So sorry, we just took away our theorem, but that's okay. Where am I trying to go right now? Maybe it's time to put in a "we want to show" sentence. It never hurts. It only hurts if you forget to say "we want to show" in front of it. It was the odd number minus the even number, right? No, it doesn't really say. But if we do in the other order, that'll also be odd. So. The difference of the odd number and the even number. We want to show it's odd. So let's do that. Well, consider x minus y. X minus y is equal to 2k plus 1 minus 2l. We want to keep in mind where we're going. We're trying to show that's odd, so we want it to end up looking like 2 times something plus 1. I think I can do this. Write it as 2k minus 2l plus 1, which is equal to 2 times k minus l, oops, parenthesis, plus 1. Are we there mostly? Here's a case where you'll see something different if you go and look in the book. They create a new variable and call it the difference, k minus l there. They're using different letters than I am too. But I don't believe it's necessary to do that. We'll just look at that expression, k minus l, and say, it's the difference of integers. And that means it's an integer itself because the integers are closed under subtraction. Sometimes I just put an explanation in by giving a little parenthetical reference to the axiom that gives it. So here we could say closure axiom. Great. So k minus l is an integer, and that means x minus y is in the form 2 times an integer plus 1. Now, something they didn't remark on in the book, but I think is kind of important, is also to have a mark that shows we're at the end of a proof. And I personally like this one, QED. That's, in older books, you almost always see them write QED at the end of a proof, quod erat demonstrandum. If the modern tendency is to not write QED, but instead put a rectangle, sometimes a filled-in rectangle, I don't know. But, you know, whatever. As long as you get some kind of mark at the end of your proof that lets people know you're done. And so any writing that appears after this is no longer part of the argument. It's maybe discussion of the argument or whatever. All right, so that brings us to an end for section 4.2. Um, Probably the worksheet for this, which you'll see tomorrow, will mostly have you be doing proofs, but maybe a few cases where I'll do the proofs and I'll ask you to figure out the flaw in the proofs, the mistake I've made. It's a good idea to be able to identify these common mistakes people talk about. In any case, I'll see you Tuesday.